Welcome to the materials recitation. We've covered lots of ways to make things, but we haven't talked about where the materials come from. We work hard in the Fab Lab network to minimize the environmental footprint, but ultimately the vision is to think globally and fabricate locally. So we have two great guides to the life cycle of the materials we're using, where they come from, and in particular, the exciting, ambitious, but feasible vision of producing materials for your lab, in your lab. So we'll go to Patricia and then Alicia. And as usual, this is interactive. Raise your hand, post questions in the chat as we go. So Patricia.
Yeah, so hi everyone. I'm glad I'm meeting you today. I'm a research scientist at the Renewable Bioproducts Institute at Georgia Tech in Atlanta, Georgia. So the structure of today's recitations that we developed with Alicia is, first of all, a small introduction on why do we care about sustainable materials, some commercially available options and suggestions for you, for your projects, for your labs on 3D printing, molding and casting, and CNC machining. With materials that you can find available in the market, some DIY ideas, and then Alicia will proceed with describing her platform, Materiom, for regenerative materials that actually brings DIY and sustainable materials to a different level. So starting with why do we care about sustainable materials? So as most of you know, materials have shaped the development of any human civilization throughout the history since the very beginning of mankind, from stone to wood to copper. The survival and the evolution of any civilization throughout history has greatly been based upon the different materials that people were using to make tools, to build their houses, to conquer nature. And every era in the human history, almost every era, is named after the particular material that people used during that time. So as you can guess, the 21st century has been named after plastics. So plastic is derived from the Greek word plastikos. I'm Greek, so that's why I'm fascinated with this stuff, which means actually fit for molding. So it refers to the plasticity that the material has and its ability to be cast, extruded, or pressed into a variety of shapes. And this versatility and unique properties that this material has, which is very durable, and at the same time very cheap and easy to make out of fossil sources, makes it actually revolutionary. And you can see here that plastic production started in the 50s. Back then, half a million tons per year were produced. Today, this number has increased by 1,000 times. We are at 500 million tons per year. And this number is expected to double by 2050. So plastics are a unique invention. It's a blessing of a material. So they can be used in a huge range of applications, from packaging to building to textiles to electronics or even transportation. More than 50% of the total plastics produced today are single-use plastics, particularly for packaging. Then synthetic fibers like polyester and nylon make up more than 60% of our clothes or 70% of the textiles that we have in our home. And plastic composites can be used for more demanding or load-bearing purposes, such as in aviation, for example. You see here the Airbus A380. So 25% of its airframe is made out of plastic composites. Plastic even made spaceflight possible. So you see here a part of the Apollo capsule, the first moon landing capsule, and the heat shield of this capsule was made out of a unique plastic composite made from an epoxy-phenolic resin and fiberglass. At the same time, plastic is also a curse because, as we said, it is a product of petroleum, about 10% of the global petroleum production nowadays is used to make plastics. And because also at their end of life, they unfortunately, they end up in the natural ecosystems in landfills, and this has huge impacts. So the one aspect of the problem are the greenhouse gas emissions associated with the production of plastics, like from extraction of oil to oil refineries, to transportation, manufacturing of these materials. So today, as you can see in the plot, on your right-hand side, about 1 billion tons of CO2 equivalent are annually generated by the production of plastics, and this number is expected to more than double by 2050. The other side of the story is the end of life, like what happens with plastic waste. So about 1 million tons per day is plastic waste generated, over 300 millions per year. And as you can imagine, during COVID, this amount almost doubled. And the sad news is that 80% of all these plastics, the waste plastic, ends up in landfills or dumps or the natural environment. And it takes too long to biodegrade, around 500 years. And a very large amount of these plastics, of this waste, ends up in the oceans. And it has been estimated that if we continue with the same pattern, by 2050, there will be more plastics than fish in the ocean. So looking beyond the current plastic era to a more sustainable horizon ahead, we need to transition away from petroleum resources to make this kind of materials into biomass sources or bio-based sources, renewably sourced materials. So these materials have the unique advantage that are locally sourced and they are abundant, like chitosan, starch, gelatin, or agar, or they can be provided by lignocellulosic biomass, sources that are all around us. And using biomass sources or renewable materials in order to make our new plastics would enable circular economic models inspired by nature, where there is no waste, and following recycling paths or biodegradable paths. And as you can see in this nice figure on your right-hand side, digital fabrication plays a key role, a central role to this transition, to this vision, as it allows for on-demand production. And by producing locally and consuming locally what we need, and avoiding long and complex and wasteful supply chains, we can reduce our waste and our emissions. So some commercially available options in order to achieve this transition towards this vision that you can easily find and work with for your projects, starting with 3D printing. First of all, it's polylactic acid, PLA. I'm sure most of you are aware of this material or use it for 3D printing at your labs. So starting from the left to the right, we have the first, the second, and the third generation of this kind of material. So nowadays, polylactic acid is produced from sugarcane mostly, or corn, or starch, so from crops. The second generation is to use lignocellulosic biomass to derive these sugars and raw materials for making this plastic. And then third generation, which is at its infancy, is to use microorganisms to convert CO2 or methane to lactic acid. And then, so PLA filaments are bio-based. They are industrially compostable, which means that they need industrial conditions with elevated moisture and temperature in order to decompose. If you leave them in nature, it will take more than 80 years to biodegrade as they are today, but they can decompose in a few months in industrial composters, and they are recyclable. So here I have some options for you for virgin and recycled PLA filaments. And okay, I will minimize the presentation to show you the different links that I have here, starting with NatureWorks, the NGO material, they have done a very good work at NGO to characterize and do the life cycle of their PLA production. So this is a well-characterized US-produced virgin PLA filament. And then Polyterra PLA, another PLA source that actually does something very cool. They plant a tree for every spool that you buy near the region of the purchase, or they claim to do so. Then recycled PLA filament from Prusa. Yes, this is Prusa. Yeah. So 3D Jake and Reflow. This comes to different colors too. And I think Reflow provides you even more fancy colors, more glossy ones. Yeah, that you can use for your projects. So moving on, apart from PLA, there is the PHA, which is 100% bio-based, produced by bacteria that ferment sugars. And because this has been microbially polymerized, it's biodegradable, which means that it can biodegrade out in the nature in about 1 year if you leave it outside, or it needs something less than 10 years in seawater to biodegrade. And there are 100% PHA filaments or even blends of PLA and PHA filaments that you can use. So Color Fab, both are Color Fab. Okay, so sorry for the cookies here. So PLA filaments, first of all, you can only find these 3 colors here, but I think the next one will give us a greater variety of different PLA PHA blends at different colors. There are also recycled filaments of other types of plastics. So there is the PETG. This is polyethylene terephthalate glycol, which is a plastic material that has enhanced durability, and it can particularly withstand chemical stressors. So depending on your application, Prusa has made such recycled PET D filament. I think it only comes out at black right now, but then this company, Reflow, provides additional options with regards to colors. And then Greengate. And then there is also recycled polyurethane, which, again, depending on your application, might be another material that you can use. I only found it in this transparent color. I'm not aware of other colors existing nowadays in the market, but if you find or know of any additional colors or materials, please feel free to share them with me. And then there are also some filaments which are composite, sustainable composite filaments. So this Filamentive, I will show it to you in a while. It's a wood PLA blend, 60% recycled PLA, 40% recycled wood fibers. So it's a nice composite material. And the same company also makes carbon fiber PETG, polyethylene glycol. And they also have carbon fiber with recycled PLA. So 50% recycled carbon fibers and 80% recycled resins. Let me show you this. So this is the wood PLA filament. And this one is the carbon fiber PET. Again, colors here are a bit limited. And then there are 2 other companies, 3D Jake and Filament to Print, which provide sustainable composite filaments. So you see here, you have a lot of options for 3D printing. So moving on to molding and casting. I found 3 interesting solutions for making sustainable molds. The first one is a glycerol/gelatin mold. So here, so there is this person, Emily Jones. So she made an excellent work in documenting her own protocol or recipe for making these glycerol/gelatin molds for molding a casting with materials she actually has at her house. And she also suggests like resources and has a very very well documented and exhaustive amount of information of how to make this at home, etc. So I highly recommend looking into this. Then there is a natural latex mold that you can make out of these materials. And then, of course, alginate mold. So this is, I think, the same company, Smooth On, that does the molding and casting material, or some of the molding and casting material that Neil actually uses in his How to Make class, if I remember correctly. So they make also these alginate molds. So moving on, some sustainable epoxy options. So this is not 100% bio-based, it's 20 to 50% bio-based. And the content is supposed to come from vegetable oils or lignin or tannins. And I have here 3 different suggestions for you: entropy resins, green epoxy, and ecopoxy. I'm pretty sure that Neil covers this in the class as well. So again, this is not 100%. Oh, they also have done a life cycle assessment of entropy resins. But it's like greener than conventional resins, epoxy resins. So all the links will be in the presentation that will be shared with you afterwards. Then with regards to computer-controlled machining, 2 cool options would be sustainable plywood or recycled acrylic sheets. This sustainable plywood option was a unique one that is out of eucalyptus, and it's an amazing piece of wood to work with. Really smooth, no toxic glues involved, no formaldehydes, sustainable development, developed forest, and then some recycled acrylic sheets here. Here it is. So yeah, it looks like regular virgin acrylic, but it's more eco-friendly. And then some DIY ideas. So some years ago at Haystack, Alfonso Pararubio, I don't know if you have met him, one of Neil's students, and I decided to make wet layup biocomposites using organic fibers and biopolymers. So there is a fun video here that we actually made. Can you see it okay? I hope so. All right. So I will not dive into all the details here, but yeah, you see how we prepare the different materials in order to make biopolymers out of glycerol and gelatin. And then we infused the fabrics layer by layer using these biopolymers, as you can see here. Yeah, the quality of the video is not the best. And then we included everything in a vacuum sealed, and you see the final material at the end. So this is a kind of composite that you can make yourselves. And then 2 interesting publications. I don't know if you have heard of superwood. So let me say it. It's not this one. Yeah. So Dr. Hughes' lab from Maryland came out with this unique material. So they published this in Nature a couple of years ago. So what they actually did is that they cooked, literally cooked wood in order to make sure that lignin is away out of the plant cell, and then they compressed the cooked wood part, and you can see that the thickness of the final piece is like 10% compared to the initial one. And by heat pressing them, new hydrogen bonds have been created among the cell walls of the plant cells. And this is why the end material is 10 times stronger than natural wood. So they called that superwood, and we decided to follow their protocol and make superwood at Haystack again in 2022. So you see again the whole process documented. Here is the cooking, like boiling the wood together with some chemicals in order to get rid of lignin. And here we prepare it for heat pressing. We did the heat pressing, and superwood that we made, and the original wood material. And this is like a mechanical testing, very like improvising mechanical testing that we did at Haystack. And then the same lab came out with this very strong lignocellulosic bioplastic material. Again, this was published in Nature. So you can see the whole protocol of how they made it. It can be made from any like wood source, and you need to add, like, you take the wood chips and you add chloride and oxalic acid and water, and you get at the end this slurry that if you apply it or form it or cast it in a different shape, you get this very strong lignocellulosic biomass film. So another thing that you can make easily is cellulose fibers out of kombucha. You see how they look like. And you can use these fibers together with a lignocellulosic bioplastic, for example, to make a unique composite that would be strong enough but 100% bio-based at the same time. So I have here a recipe for making your own kombucha and growing your thick kombucha mat. This cellulose, bacterial cellulosic mat that actually has all the fibers that you might need for your composite. So that's all from me. And I am giving the floor to Alicia. Would love to discuss further, and if you have any questions or any new suggestions, I'd like to improve this content. If you have any, please share them my side. Thanks.
Thanks, Patricia. I'm going to now share my screen. So hello, everyone. My name is Alicia Garmalevich. I'm a professor of circular economy at the University of Santiago, Chile. And I'm founder and co-CEO of Materiom, which is a platform that helps to lift up the bio-based material sector and help accelerate R&D in the space. So today I'm going to give you a little bit of an overview of the motivation for why these materials need to be supported to come more and more to the fore and to be more available, in addition to a little bit of a tour of the platform, as we have resources available for anyone who wants to use them for their own research and development for in this materials in the material space. So to begin, I'd like to invite everyone to imagine a world where plastics are plant food. Similarly to what Patricia said, there is immense potential in the bio-based material space, specifically those that are compostable and go back into nourishing soil. And it's driven by a huge imperative that we need to get off fossil fuels writ large, and that includes the materials sector. Often we don't think about climate change and plastics being one and the same challenge, but they're certainly intertwined. And we, in order to reduce our not only the contaminants that are in our environment and in our bodies, we also need to reduce our impact on the climate. So that's part and parcel of why these materials should be invested in and supported, in addition to there being an exciting research and innovation frontier. So what are we talking about when I use the term regenerative materials, or we do at Materiom? And the point of doing that is to differentiate from a very mixed bag of terminology when it comes to bio-based, compostable, biodegradable. A lot of people use these terms and it's very difficult to know what they actually mean. So bio-based can mean a certain percentage of bio, for instance, with a lot of petroleum plastics in there. Compostable and biodegradable can mean non-bio but are biodegradable, for instance. And so there's a large kind of matrix of terms that it's difficult to sift through. So we use the term regenerative to mean 100% bio-based, 100% biodegradable, and sourced from biomass that doesn't compete with food security. That latter piece is super important because, as Patricia mentioned, there's quite a few sources on the market today that are made from corn or soybeans or sugars that come from primary crops, basically. And those primary crops are competing directly for food security often, or at least there's large land use change that's associated with their investment and adoption as kind of a quote unquote solution for the materials sector. So by contrast, there's a huge amount of untapped biomass when it comes to the utility for the materials sector in agricultural waste. So leaves, stalks, husks, stems, industrial byproducts. This also includes, for instance, like just the production of food stuff. So for instance, if you're going to have a tomato paste factory, huge amount of tomato skins are just wasted in the process. And those are the kind of point source that you can actually get a lot of pectin, for instance, which is a very valuable biopolymer for making films and coatings. Non-competitive biomass such as seaweed and mycelium. There's some beautiful materials out there on the market now from both those that are actually showing quite a good amount of cost competitiveness and performance for the bags, coatings, packaging space, as well as textiles. And then unavoidable food waste. So all the stuff that we can't ingest ourselves, coffee grounds, peels, pits, again, huge amount of potential for sourcing. One of the issues there is they're very non-concentrated in terms of where this biomass is. So it's often an economic and logistical challenge. But one of the interesting points is it's also a data challenge. So even if you wanted to source from multiple sites, there's often variability in the chemistry of those polymers, and understanding that variability is really important to be able to control for it for the production of materials. So that's an interesting area of scaling up these materials that we see businesses wrestling with today. And to go to the bigger picture in terms of this bigger shift, Neil touched on it. So the idea of Fab Labs being really at the center of this larger shift that we want to support is from a centralized fossil-based economy to a decentralized renewables-based economy. It's very easy to imagine this transition when we look at the way that renewable energy has transitioned over the last few decades. It used to become kind of, it was inconceivable that energy would come from what's around you. Now it's pretty obvious that you can have different mixes of the energy mix. So, you know, where the wind blows, where the sun shines, depending on where you are in the world. Similarly, we see the biopolymer space needing to follow that transition story and looking at where different biopolymers are available, depending on different types of industrial mixes, different growing conditions, etc. So that's the kind of overall switch that we are looking to support. And the production of goods from those local sources of materials is where Fab Labs specifically interweave with this local or regional materials economy and the development of supply chains that can support it. So where does Materiom fit in? We're an innovation platform that really helps new entrepreneurs get off the ground and start experimenting with these materials and start to develop their first proof of concept, and then hopefully develop it into a viable material solution for whatever product space they're wanting to tackle. So we have started our journey with developing an open access database that's available to everyone free. You can just log in and view everything. We're working on loading in more and more material recipes, specifically from the open access scientific literature, in addition to developing and cultivating a community who are interested in sharing and supporting each other by offering the recipes, some of which, you know, Patricia touched on, that you can make in your own Fab Lab and contribute those to the community. There's now about 11,000 users in the community. So it's starting to be very rich and vibrant when it comes to the kind of geographic mix of people and the activity that's happening there. The other aspect of what we're working on now is an AI driven application that can help biomaterial entrepreneurs find a material variation or a new material that meets their performance specifications faster and more efficiently. We're working with Google in order to develop that right now. And that's going to be something where we aim to develop a proof of concept that we can show to our users over the next 6 months. And again, the idea is to just make this whole development journey of new materials much more fast and efficient than it has been. Basically, we're up against 100 years of R&D in the petroleum plastic sector. And in order, we don't have 100 years when it comes to reversing trends of climate change and plastics pollution. So we need to reduce those by factors of 10 or 100 in order to get to material solutions that work. And then finally, we convene a lot of folks from different parts of the value chain in order to kind of bring together solutions and help them scale. So I'm going to touch on a little bit of Materiom's Gen AI just to showcase what we're like the frontier of what we're doing, but then I'll hop to our database and showcase what we've got today that everyone can use and participate in right now. So as I said, the Gen AI is designed to provide biomaterial recipes for our community. And specifically, we're thinking of two main users. The first is material SMEs and brands. So they're trying to meet performance targets and impact targets, helping them do so with suggesting new recipes faster is where that's at. And then also scientists and educators who are trying to generate novel materials for research applications. An example of our idealized user, actually it's not idealized, we're working with Banoffee on testing the Gen AI right now. But an example would be this startup out of India who's developed an amazing bio-based leather from banana waste. So the stalks and plant refuse that is there when bananas are harvested is usually burned today. And they've made an amazing leather-like material from that waste biomass. And what they're struggling with is trying to make it 100% bio. So there's often a little bit of petrochemical plastic in there in order to like make it super flexible or make it more durable, etc. And that's where the kind of R&D is necessary in order to try and find that 100% bio-based recipe. So that's the kind of use case that we're aiming to help with this technology. All right, I'm going to hop into the dashboard. Can you guys see the Materiom dashboard? Great. Okay, so this is what you'll see if you log in. It's just a free login. You can see here, you can see my dashboard. There we are. With this dashboard, you can view and make contributions. So if you wanted to upload a recipe, you can create a new one, contribute to an existing one. I'll dwell on this for a second because it's super important. We're trying to utilize some of the infrastructure tools that we've seen work in the open source world of open hardware and software, where you can fork and remix and add to existing code, for instance, instead of just contributing like a completely unique recipe. What you can do is take someone's existing recipe and say, okay, maybe I want to test this tensile strength of this, and you add a data component. Or you add, say, a picture of an application that you've made with that material. Or maybe you just duplicate it and you actually add, I've made it too, and that's an entirely valid contribution as well. So the idea is to kind of create the community infrastructure to grow the biomaterial sector faster by virtue of working together and the collaborative nature of that. You can also go into the user directory and see everyone all over the world who is part of this movement, and view their discipline by industry and filter that. We're going to be adding to this quite actively in the next few months in order to help users have more customizability around their user directory and be able to connect with each other more faster. Sorry, this is I think it's maybe the Zoom interface that's slowing this down, but I'll try and go back to the dashboard. Here we are. All right. And then you can go into the materials database. So the materials database is where you can see all of the recipes as soon as it loads up. Come on. Yeah, it's coming. And this is where you can see both, as I said, user contributed recipes, as well as those we've loaded in from the scientific literature. Come on. Sorry. Why it's so slow. While it's taking its sweet time, I'll mention the fact that one of the things that we're going to be working on shortly is integrating.
Alicia, do you want to show on my screen if that's not loading there?
Sure. If it's well, I had it all loaded up to showcase some of the data stuff. Let me just. I think it should come in just a few seconds. Okay. It's almost at the end of the load bar. But yeah, let's switch if it doesn't work. So yeah, I was just going to mention that what we're doing is we're speaking a lot now to entrepreneurs who are now converting their proof of concepts into real companies that they're trying to get off the ground. And so we're going to be also integrating users who are interested in marketing their new materials to anyone who wants to use them, including, Fab Labs or commercial brands or what have you. And that's a really interesting evolution that we've witnessed that has happened really just in the few years we've been a part of this space. So yeah, it's not working, is it? Okay, let me try one more time and then we'll shift over, Neil. All right, I'll stop sharing, and maybe if you have it up, that would be great.
Sorry, let's see. I guess this is for other people. I'm running into it wants me to have a materials commons login.
Yeah. Let me.
I do have a profile, Materiom. Do you want to share through mine?
Sure, that would be great.
I don't have contributions yet.
That's fine. It would just be easier if. What I can do is also just load it up again to see if it works. better.
Okay, let me know, where do you want me to go?
Let me see. Okay, so if you go to the materials database, perfect. You can choose materials to graph if you want. So you can choose by ingredients or processes that you're interested in, that will select those. You can also do a keyword search for any that you're interested in. But if you go into, say, that one, methyl cellulose bioplastic right there, you can see what it looks like. So you'll be able to see the tools, the processes, the prep time, the composition, the method of making, and then images if the person has included that. You'll also be able to see, for those recipes that have tested properties, the properties of those materials. I don't think this one has any. Nope. So this is an example of, if you wanted to contribute to this recipe, you could add that component of the recipe, and it would showcase that you being the author of that part of it, so that it kind of becomes a collective enterprise, these recipes. So thanks, Patricia. If you could go back to the materials database. Great. And let's see, so if you hover over the chitosan oxidized nanocellulose, yeah, let's take a look at that one. Oh, sorry, go back. So you should be able to, there's a little plus sign on the right corner of them. Yeah, can you see that?
Yeah.
Yeah, so if you do the plus, yeah. There you go. And then just graph material on the top. No, not clear, graph. There you go. Yeah, so this is an example of what you can now see in terms of the property landscape. So you'll be able to see, in this case, there's 11 variations of this recipe, which means that the authors have changed the composition, so the amount of chitosan versus nanocellulose in different proportions, and that relates to different properties that the resulting material has. So you'll be able to hover over any of those dots, and the dots are the individual recipes in terms of their performance properties. And you'll be able to see tensile strength versus stiffness in this case, and zoom in. And you'll be able to, if you want to graph other recipes against each other, you can also select a bunch and then graph them relative to each other.
Alicia, what are the units on that graph and how were they measured?
So in this case, I believe it should be megapascals in terms of tensile strength. Stiffness is a good point. I would need to go into it's a perfect feedback for the graphical interface that we need to improve on. So thanks for pointing that out.
And
then how are they measured?
So that would be down to the individual paper. So one would need to then go into that recipe and look at their methodology, which is linked in each case. Yeah, so this is not a standardized, approach by us. It's rather collecting individual studies that have been done. And that's one of the things we're aiming to do, or we have the ability to do, is if you are contributing a study, you can include things like the machine that you use to do the tensile tensile tests on. You can do even the humidity in the room, for instance. There's a lot of additional information that we have the ability to add in terms of metadata in order to improve replicability and trust in terms of these data points. But often these are not reported in papers, so it's something that is an ongoing challenge to reproducibility of material testing. Yeah, thanks, Patricia. That's all I wanted to show. So I welcome anyone to have a look, have a poke around and contribute or use any of the recipes on our site. We are looking at a public launch in a few months that will include a large additional set of data that we've been working with natural language processing to extract through data mining. That's going to be coming down the pipe. Yeah, so I look forward to any comments or questions, and I think Patricia the same. We can take questions for the remainder or however much time, Neil, you want to allot. But thank you for your time.
Start with one.
Just a sec, before moving on, do you want to share a bit our paper that we published last fall?
Sure, Neil, does that sound like a good use of time?
Please do that, absolutely.
Okay, sure. Yeah, thanks, Patricia. I had forgotten the tail end. So here we are, slideshow. So Patricia and I had the good fortune of working on this study together where we looked at the Great Lakes region, specifically looked at biomaterials that could be used or created from sources of waste. And we specifically looked at the linkages between biomaterials and regenerative agriculture, because agriculture, as I said, is a large source of potential biomass for developing regenerative materials in terms of waste. However, agricultural practices today are incredibly degenerative often. They are very exploitative of the soil. And they require a huge amount of chemical pesticides, et cetera, as inputs that is very damaging. So we looked at, by contrast, regenerative practices that do a lot of different kind of approaches to agriculture, and they often keep a lot of biomass on the land. They often use organic inputs rather than pesticides, and there's a lot of different aspects to it that change the nature of the linkage potentially between biomaterials and regenerative ag. So we, yeah, as I mentioned, these are the principles of regenerative agriculture, such as keeping the soil covered with living roots, minimizing soil disturbance, and that changed the kind of nature of how materials fit into this picture. And what we basically found was that on the one hand, there's still a sizable amount that you can take off of farms after the crop has been harvested. Specifically, materials like cellulose and cellulosic monomers are quite in abundance, and around 20% can be taken off without damaging or interacting with the needs of regenerative agriculture. And then when it comes to the materials that the potential of residues derived from these systems, we also looked at kind of polycultures, so not just monocultures, which does have a problematic interaction with increasing the amount of pesticides needed and the soil degeneration that happens. But there's a lot of other materials, biomaterials that can be made from plants that specifically are integrated for polycultures that can help with pest control, that can help the soil in its fertility. And here's just an example of some of the materials that were identified that you can create from some of these crops that can have these ecosystem services. And importantly, we also looked at the return loop. So imagine that a biomaterial made from various biopolymers was then used as fertilizer or input to the soil to increase the potential of that agricultural system. And we looked at specifically the essential crop nutrients that could be released from various types of materials. So here, for instance, walnut shell and mycelium composite, eggshell chitosan, carrageenan films from algae, gelatin bioplastics. These are the kinds of materials that we looked at the crop nutrients that are produced. And what's really exciting is that there are certainly high levels of certain nutrients that could provide very important crop amendment potential, which I want to emphasize, because a lot of our focus on quote unquote alternatives to petroleum plastics are for the materials to kind of go away after end of life. The idea is to just make them disappear or have as little impact as possible. This changes that framing quite radically, and we need to start thinking about these materials as benefits for the systems that we have after end of life, and thinking about them as actually valuable. So we've been talking to, say, industrial composters in terms of like, how do we view these materials as a value add to their compost? And they actually would want to then create a market pull for these materials to be integrated into municipal systems, for instance. This is the kind of valuation of the materials at end of life that we need to get to. So this study was a good step in that direction to really understand how these could be valuable for agricultural systems. Okay, thank you.
Great. So that's a great vision of the waste from your lab doesn't go in the trash. It goes into the field around the lab to feed the crops. So do you have metrics? So revolutions start exponential, eventually become sigmoid. What's the pace of adoption?
That's a great question. So what we're seeing right now is a clear exponential when it comes to the startup space. So on both sides, one is that the number of people getting into the biomaterial space is definitely taking off, but in particular, the number of, say, innovators who are researchers or just makers that are starting to create a startup that actually develops a material that they want to commercialize, that is going through the roof right now. So we can't even keep up when it comes to trying to collect examples of these companies. 10 years ago, there was just literally a handful, and now there's hundreds. And there's every time you look at a new region or a new part of the world, there's more that you find. So that is something that we're very excited about, because it showcases that it's getting into more sophisticated territory as well, that we're looking at these materials not just being able to make yourself, but you can actually purchase, and that brings in a whole nother element of potential utility. So that's one of the maturity of the market things that we're looking at. The second is there's increasing examples of these materials getting to scale, in quotes. One of the ones I'll just spotlight, because it just happened, is a company called Sway Bioplastics. Here, I'll just screen share for 1 second. Is that they just closed a $5 million seed round for their resin called TPC. It's made from 100% seaweed-based biopolymers. My computer obviously is struggling right now. Here we are. And what's great about it is that it's a resin that is specifically targeted or integratable into current plastics infrastructure, which means that plastics converters, plastics compounders, this is a format and like a resin that they can actually work with. It's not something that, often when you make something by hand, it's very difficult to then say, okay, give it to a converter in what format for them to scale and make these materials at an industrial level. Whereas this, they've cracked, this has been a big push for them over the last 10 years, but they've cracked a format that allows them to scale through existing plastics infrastructure. So this type of thing is really exciting and novel in this space, that we're starting to see the ability for companies to get to scale.
And just to provide some global numbers, so I was reading the other day that currently the sustainable materials market is about $10 billion, US dollars, and the compound annual growth rate for the next decade up to 2030 is 20%. So it's anticipated to grow exponentially. So I think, like using the terms that you just described, Neil, we are in the beginning of the exponential curve.
Yeah, it might be interesting to vet the Fab Academy curriculum to come up with a guide to how much of it you can do locally sourced, and each year try to move that fraction. Marius is asking about antibiotics or antifungi like cinnamon in humid regions where things take more time. The question is about the need for antibiotics, antifungi.
It's a really good point that a lot of these materials in the practice of making them have the issue of fungal growth. So I don't have off the top of my head a great list of things that one needs to do, but there's certain ways to control the environment. There's certain ingredients. So it sounds like a really, it's a really important area that needs to be tackled more and more. So it sounds like a great starting point for that investigation if you have already some antifungal ingredients in mind.
Any other questions? We're almost out of time. Let's see. I should note there's a neighboring project on open metrology, and we've collaborated with Alicia on like the machines making machines, open versions of things like tensile testers, because the measurement is an important part of the materials development, an essential part. I'd say
Yes.
on balance, there's lots of squishy, soft, sustainable materials. There's fewer stiff, strong, hard, sustainable biomaterials.
Yeah, I'd call your attention to FLAM as one. I think I've mentioned this in the past, Neil, but we can add some links to you later. That's a really great one that combines cellulose and chitin. And out of Javier Fernandez's lab at Singapore, in Singapore, he came from Harvard Weiss Institute and has led that it's a very kind of moldable, strong material that is 3D printable as well. So a fascinating material. So I'd really recommend checking out that, but it's certainly, there's also bricks that are made from bacterial, I'd have to look up the company, but there's a few like cement-like materials that are out there as well in the built environment. But you're right, it is dominated. I would just say that it's also really important that the kind of single-use squishy materials are some of the biggest culprits out there. So it is a big space to tackle, but I quite agree that it'd be great to see more high performance hard materials as well come.
Let's see. Alejandro is asking about cost accessible. I mean, I think about them tending to be more expensive. I think that the heart of the cost accessibility is not commercial production, but local production.
Yes, and specifically tapping into waste. So this is where it becomes really interesting from a cost competitive perspective, is if you're able to tap into waste and actually valorize that, that is a really impressive route to potential cost competitiveness.
Yep, many of the examples Alicia gave are turning bugs into features of things that were a problem to get rid of, that people would pay you to take away, that then become valuable materials, and both for you to use and inputs further downstream. So we're up to the hour. View this recitation not as forward-looking, but an invitation to the present. If you're at all interested, this is something you can start doing right away. There's a ton of information and a lively community. Okay, wonderful job, Patricia and Alicia. Thank you.
Thank you for inviting us.
Thank you very much for having us.
And yeah, for all the people clapping, the way to thank them is to join in. They're really driven and helping drive this transition. The way to thank them is to experiment, contribute, join the movement. Okay, and with that, thank you, and I'll stop recording.